Hello everyone and welcome in this new tutorial episode on WebGPU. Today I would like to talk about the journey I took lately trying to build a WebGPU application with Emscripten. So to get a WASM application that you would then run in your browser. So first question I guess that some of you may have would be, why would you want to do that? Because you can in fact already use WebGPU itself directly in JavaScript. So you can build a JavaScript application with WebGPU and run that in your browser, or most probably you can just use a TypeScript interface also for that. But still, from my perspective, it can still make sense to build a WebGPU application with Emscripten itself, because then you are going to build your application with C++ or another language that is not directly available in the browser itself. And if you are like me, for instance, you maybe just really like to work with C++ and you maybe are not that gifted with TypeScript or JavaScript. So in this case, it definitely makes sense to use C++ directly to build the application you want and then to compile that with Emscripten. So yeah, let's just get started. First, let's start with a quick overview of the result that we're going to produce here. This is, for instance, the final result that we get trying to run the application as a WASM application, so in your browser. In this case, this is running in Chrome. So you see that it's actually opening a web page here. I'm not quite sure we can do anything to verify that this is actually a WebGPU display, but yeah, just trust me on this point. And here is the same application running as a native application. So this time it's built with a dedicated native window, still using SDL2. We're also using SDL2 in fact in the WASM version, but you don't really see that in fact. And now let's see how we're going to build this app. There will be 4 key sections in this recording. So first we're going to see how to build a very minimal SDL2 test application, a native test application, so building that directly on Windows in this case. Then we're going also to check how to move to an Emscripten compiled version of a simple SDL2 application. And after that, we will try to use SDL2 and WebGPU, but only for the native version first. So we're going to rely on the down library when you use the native version of WebGPU here. And finally, we're going to use the code that was written for the step 3, and we're going to extend on this code to also provide support for the Emscripten compilation, and this will give us a final application that can be built natively or also as a WASM module. Now, to keep those recordings not too long, we will split this tutorial in 2 parts. The first part, which is the current video, will be covering only the first 2 steps. So we will be mainly focusing on how we will integrate SDL2 into WASM. And then the next video will deal with the step 3 and step 4. So that second part will mainly focus on the introduction of the WebGPU framework into the base application. Alright, so as I said, the first step that we're going to discuss here is the SDL minimal application. So this is the one that we are building natively. This is built actually with a single file, this main CPP file here, and the content is pretty small. You can see that we have a structure definition, for instance, at the beginning, but it's not really relevant yet because I was already trying to integrate Emscripten at some point, but I eventually just removed this part. So this application is really only going to build with the Visual Studio compiler or C9 compiler, but not yet with Emscripten. And the main function here is not doing that much. You're going to initialize SDL, then just create a simple window and then you enter your main loop, in fact. So with the poll event here, that's where you would then be rendering some content, but in this case I'm not even rendering anything. So as you might guess, this will only produce an empty window, a black window, and eventually when you are done running, you just destroy your window and you do exit. This is the corresponding cmake file used to build the application. So the name I have is test SDL_minimal. There are some lines that are commented because at this point we don't really need any dependency on the NVL libraries. So you can in fact build this test application probably without too much trouble. You only need the dependency on SDL itself, then you just provide your main file here. This part is not relevant. As I said, I was doing some tests initially, but eventually I just stopped trying to build with Emscripten, this minimal version here. So that's not being considered at all. Then you just prepare an executable, link with your libraries, and that's it. Again, this part here is not really effective, so not relevant, but we're still going to use those functions here at some point later when we are going to build with Emscripten. Next, to execute this test application, I have in my nerve approach mechanism a dedicated script NVL SDL_minimal, which is going to execute this application in this folder. So this is what we can try, and as you can see, that's just going to produce a completely empty window, but that's a start anyway. Next, we move to the test SDL WASM application. So this is the second one, and this one was made focusing on the Emscripten support. So it's not even going to compile properly with Zlang or Visual Studio. And let's see what we have here, which is different from the previous one. We still have the main function. Also, something I didn't mention maybe in the previous one, but it was already there, I think. Yes, this part. This is something that I was testing at some point to get access to some asset files, but it turns out that it's not really necessary. So this section is completely disabled for the moment, but you probably want to keep in mind that you have the possibility to execute some JavaScript code directly like that when you use Emscripten. Anyway, what do we have here? We still have this context structure, but this time we are really going to make use of it. We are going to initialize SDL and create a window as before. We have a simple renderer in this case. I don't think we had this one in the previous code. No, not really, because the window was completely black. And then yes, this is in fact the only reason why I have a dependency on the NVL core library in this test application. So you see that I'm including this core common and using this namespace, and in fact in the cmake file we have yes, we are linking to this NV core light library because we need to check if a file those exist. There's probably a function to do that directly in a more standard way, but I was a bit lazy, so I didn't change that. That would be an easy fix anyway. So we're going to figure out if the file here exists, and it should really exist, and that's the SDL bitmap, which we have here. And in fact, I was really only checking for existence of the file because I had a problem initially with my assets and I could not find this bitmap. But now that everything is working fine, you don't really need this code here. Next, we're going to load this bitmap and create an SDL surface from this. We turn this surface into a texture, and this texture will be stored in the context structure. And after that, we have what is the main difference, I would say, when you get into the Emscripten world compared to a native application, which is that you don't really have direct control on your main loop anymore, because the main loop is really going to be managed by the browser itself. So the browser is going to tell you when you get a chance to execute one step of your main loop. So that's why we need to call this Emscripten set main loop with argument, and the main loop function here will be the callback function, and this one is going to accept an argument which is a pointer to the context object. I'm not quite sure how Emscripten is dealing with this, and because basically you have to assume that this call is going to block and you're not going to continue and execute the following functions here, but maybe that's not exactly how it works. I feel I've read something that was a bit strange on this point, but never mind. Let's just have a look at the callback function maybe. So in there you just retrieve your argument, convert that as a pointer on the context, and that's where you have a chance to collect all the events that occurred since the previous frame. And another event that we have here is in case we're pressing a mouse button, we're going to move this rectangle by 20 pixels on the x-axis. And after that you clear the rendering, you set render draw color, that's a white color, render fill rectangle, that's how you're rendering your rect2 with the draw color which is white here, I guess. Then you set another draw color, render copy of the logo, so the texture that you created from the SDL logo, and you render that with this first rectangle. And finally you present this frame. So as you can see, the code itself is pretty small and pretty easy to understand, but now we have to consider how we're going to build that and how we're going to run this WASM application. So first, for the build process, in my case I can simply use the build command for the full Nervland project and specify that I want to use the emcc compiler. So everything is built here already, but if I make a change, for instance, in this file, you get a better idea of what's really happening. Okay, so building the main file, and it's going to install the GS file, the WASM file, and the data file. So let's have a look at the cmake file for this test application now. So in there, everything here is pretty standard, except maybe the suffix that you have to specify for your executable. Normally for your regular application that would be a .exe on the Windows and nothing on Linux, but when you're building a WASM application, you really just have the choice between GS, so JavaScript, or HTML. If you use HTML, the Emscripten compiler is still going to build a GS file, but it's also going to produce the HTML file that will encapsulate the call to load the corresponding GS file. In our case, we took a simpler option, which is to just produce a GS file, which, by the way, is itself going to load the WASM file, and we're going to write the HTML file ourselves. So we'll get to this point a bit later. Apart from that, we're still going to create an executable, link that to some libraries which must be built with Emscripten, and this is really where we have Emscripten specific settings. In this case, for instance, we're going to specify that we want to provide this SDL bitmap, which is available here as an asset in the build folder, and we want to provide that as an asset to the WASM application itself. So we have to preload this file, which means here that it's going to take a copy of this local file and make it available as this path, as a well, using some kind of a virtual file system. And to be honest, I don't really remember why I specify no heap copy here. Maybe it's not really needed here. Then we have this function, setup inscripten SDL target, which is providing the target name and the link flags. And so here is the setup inscripten SDL target macro, and it's going to provide some additional link flags, some that are really, well, what I consider default link flags for Emscripten, and some that are more specific to when you want to build a SDL based application with Emscripten. And then we have this additional function also, which is going to preload the Emscripten assets. So let's see what each of them is doing. Get Emscripten default link flags. So this one is going to set a default value for your init memory in case you're not providing one, and providing by default all those additional flags. So you want to produce a WASM module in the end, maximum optimization, allow memory growth. Okay, I could go with explaining some of those entries, but that's going to take a long time. So this is really just to give you an idea maybe of what kind of settings you could use. For instance, here also you have some values that I am enabling by default, but we're not going really to use that because we're not using WebGPU. And this is the one also that I need to have support for the virtual file system. You have a few different options on this point also, but you definitely want to check the documentation from Emscripten to get more info on this point. Force file system, well, you probably don't need that if you are trying to access a file system, like in this case, if you check for existence of a file, if you try to load something as a file, it's going to include the file system support normally, but just in case, I'm just specifying that to 1. Now, concerning the SDL specific link flags, what is really the key here is we have to disable pthreads. Yes, I remember that when I was trying to build with pthreads, I think there was something not working, so I disabled this here. Then you enable the usage of SDL version 2, and since we're going to load a bitmap from the file system, you have to enable this use SDL image. I guess that's also version number 2, and you need a list of the image format that are supported. And if you pay attention to this formatting here, yeah, it's a bit strange and tricky, but I think I've seen that somewhere, but I have no link here. That's working anyway. That's how you need to write the argument, at least when you have a single format. When you have multiple formats, it's a bit different, I think. Finally, it is preload Emscripten asset macro. This is a bit more specific to how I am usually building my WASM test application, but it's not really needed here because I'm processing a bit differently with the preload file specified directly as an initial link flag here. And we also have this install Emscripten targets, which is going to always install the GS and WASM target files in your destination folder. But in some cases, you may also have the worker.gs. If you have enabled the thread support, then you're going to have this worker.gs file, and you may also optionally have the corresponding HTML file if you specify that Emscripten should generate the HTML file, and the data file if you have some assets that you want to preload, but otherwise those files would not exist, so that's why you have to consider this as optional. Now, concerning the execution of this test SDL WASM application, I have a dedicated script again, which is using in fact a Python module and using the folder corresponding to this application to request the start of a Firefox process pointing to this location. So the good thing is that this Python module here is available as part of the MVP project, so the NERV project, And this project is available directly on GitHub, so you can go on my repository here to get access to those Python modules. And in this case, this is the one that you need to have a look at if you want to see how we're processing this loading of this WASM application. In fact, loading a WASM application that you are building locally can be a bit tricky if you're not used to it. So you probably want to try to use this function somehow to see if this helps, because you have to be careful about some consideration, like the fact that you may need a certificate, an SSL certificate, otherwise support for the WASM execution will not be enabled in most browsers, except if you use the local host as the server, in which case you may not need a certificate. So you have some consideration here that maybe not that obvious initially. But anyway, if we now try to execute the corresponding script, oh yeah, okay, it's going in fact to compress the WASM module that we built with broadly, which is not really necessary here because we are still really just using the uncompressed version of the module. But if you were to serve this application in a production setup, you probably want to use compression on your WASM module. And this is the final display that we get. So you can see that we have the canvas here, which is the SDL canvas. You have the title here coming from SDL, and this is a white rectangle 2. And if you just now click on the canvas, you can see that the event is handled by SDL, and you have this movement that was discussed previously. And if we go below the image, we see that the transparency of the bitmap is still taken into consideration. So yeah, this is it for the second step, the SDL integration into WASM. Now let's move to step number 3. Before we move to the step number 3, one thing I forgot to mention is this HTML file that we are, well, actually generating ourselves to load the SDL WASM JavaScript file. So you see that it's pretty simple. We just have a minimal body here with centering the canvas, and we are going to, well, load the script this way. I'm not even sure in fact that we need this part. Maybe it's enough to just include this script here. This is something that may be worth testing. Let's try in fact to just comment this part, save, and try to load again. Well, no. Doesn't work in this case. Let's see. Canvas is undefined. Okay, so we really need this additional script then. Alright, anyway, it's on this wonderful failing test that we're going to stop this first part of the recording. We have only been discussing about the SDL2 introduction here, and as I said at the beginning, in the second part we'll be focusing on the introduction of the WebGPU framework into those basic simple test application. But this is going to take significantly more time in fact to discuss those additional test apps, so we'll put that in the second part. If you have any question anyway on this first part already, just let me know in the comments, and otherwise I'll see you again next time for the second part of this journey. So meanwhile, have a nice time on your side, happy coding, and see you very soon. Bye bye.